Thank you, everybody, for joining. My name is Shahzaib. I have been working with Colossian for over 4 years now. And a lot of my background, I started off in deep learning with mostly predictive computer vision. So I was working with object detection, segmentation, and all of the downstream applications that come with it. I started in generative AI when I joined Colossian, and we started off with the very different kind of tech stack. And back then, there was this very interesting way of producing realistic texture called deferred neural rendering. And since then, the space has evolved a lot. And I would love to basically share a little bit about how the recent advancement in generative AI are powering the creation of avatars. And I would also like to show how it's gotten much more scalable and how complicated and complex the avatar creation process was and how much it has been simplified now thanks to generative AI. A little bit about Colossian. Colossian is a product which helps you create really engaging videos with AI presenters. And you can put together a video really quickly with the drag and drop functionality. And it helps you also create videos out of your documents through a prompt, and then helps the whole video creation, makes the whole video creation process much more easier than having to go into a studio, record an actual actor, and then all the cost that comes with it. So yeah, it's a very useful, a very efficient way of putting together videos. And that's basically the main technology stack that me and my team work on, is the creation of the avatar process itself. So let's start with how that happens and what it entails. So it constitutes two main things when we talk about, human clones or avatars. It involves modeling and animation, because whenever you want to replicate a human performance or someone's likeness, the modeling will entail the geometry, the facial structure, the appearance, which will be the texture, and all of the details that are related to that. And then the second step would be animation. So once you have figured that out, you would like to have a process with which you can animate that modeled human head, for example. So you would like that, you would like to change the pose or the motion or the animation or the facial expression and all of that. So essentially, this boils down to these two very important building blocks or components. Let's start with how this was conventionally done, or is still done actually in Hollywood. This is still the way to do is modeling this, the likeness or the facial appearance is a very intricate and manual process. Or this is how it was majorly done using tools like Blender, Maya. You would have to map the facial structure of a person, and that at the end of all this, you would get a 3D mesh. Now that mesh represents the facial structure of that particular person, and all the details related to the geometry. This process can be made much more simpler with the help of something that's called face models or 3D face models. Basically, the human face shares a lot of similarity. So a lot of, if you want to collect a lot of different faces, you can essentially map them into a much more lower dimension than the set of vertices that we were trying to put here. And the fact that we can do that is because our faces are very, very similar, and there are very little variations that exist there. And by making use of this fact, you can essentially record a few, thousand people in a 3D scan facility. And once you have those scans, you can essentially map the full facial structure to a much lower dimension with the help of a PCA or any similar technique. And then at the end of the day, if you do this, what you get is a lower dimensional vector and a vector space with the help of which you can change the shape of the face or you can manipulate it to change the facial expression, right? This is how you come up with a face model. And once you have this, the first process that I explained becomes much more easier. Because now you have a person from different angles, for example. With the help of this face model, you can just tweak those vectors that we learned in the previous step, and then you can make the whole fitting process much more easier. And then you learn the geometry of the person. You can actually go beyond that and use any landmark detection or the dense landmark detection tool to actually spot the region of interest on the face, and then have your face model match that. And the face model will optimize to kind of fit those details that the landmarks is providing, and that's how you will get your face model that is fitted to the person, right? Now, once this face model has been fitted, the very next step is that we want to animate it, right? Because we want to get the talking head out of this whole process. Once this fitting process is done, to be able to animate it, there are like two ways you can get around it, actually. The one is called the performance capture, for example, is a very trivial way of doing it, meaning that you drive that generated head that you just generated through another video of a person. So whatever expressions or facial animation the person was doing in the video, it will be projected to the 3D face that you just encoded. A better way to do this is train a neural network that will get an audio signal as an input, and then from that audio signal, you can drive your face model that you just learned. Now, this whole process is actually how our legacy pipeline was built. It was built powered by 3D face models, driven by a neural network which was conditioning the expressions, and this network is actually going to predict these PCA expressions that we learned here, and then you can just animate that head, and that's your avatar. But now, with the recent advancements in generative AI, especially the diffusion models, a lot of this process can be made much more scalable and then much more simpler. Now let's start with that and slowly build it towards how we can use this to create this avatar pipeline that I just discussed. I would like to start with really quickly establishing a base for what generative AI is, especially in the context of vision models and diffusion models. So there are multiple ways to actually build a generative model. The one that we are discussing here is called flow matching. Why it's called that, I will try to establish a context there. So the model is essentially, at the end of the day, is trying to map one distribution to another. That's the actual problem statement that it tries to solve. What that means is, as you see here, we have two distributions. One is P and the other is Q. So with P, we call the source distribution, and Q is our target distribution. The Q, which is our target distribution, is actually the distribution of our data. So for example, if I were to pick any random point from Q, it will give me a valid image. So in this case, you see, we sampled a point here and it was an image of a dog. And if I sample a point anywhere else, could be image of a car, image of a cat, image of anything, right? So it's a valid looking image, this distribution. And we start with another distribution, which, as you can see, is noise. So this source distribution technically can be anything. But in practice, we love to start from a normal distribution because of all the nice properties that it has. So you see, we pick any random point, we sample it, and then we want to arrive at the picture of that dog. And that generative model is going to do is it is going to transform this distribution into Q. And as you see, the path design and then the training process, and at the end of the day, we have the sampling. This is basically how the flow matching works with generative AI models. But I would love to share a little bit more about how this happens. Before I do that, one thing that we do in practice, so here you see we have an image of a dog, and we are starting with a very, very noised image. But in practice, working with actual image is very, very computationally expensive, right? So what we usually do is we compress that image and we compress it into a much more lower dimensional, usually the orders of thousands, lower dimension. And once we compress it into the lower dimension that you see between that encoder and decoder, with the help of that compressed, which we call a latent vector, we can then project that image back, right? And the fact that why we are able to do this is because a lot of the actual pixel information on the image is redundant. The infinite many combination of pixels that you can generate will usually result in a noisy image. So a valid looking image is a very short subset of how the pixels can be oriented, right? So it's very convenient that we can project all of that useful information into a very, very small dimensional vector. And what we do is actually we get a noisy vector instead of what we were doing here, which you see is a noisy image. Now we have that noisy vector which we have compressed. And with the help of that noisy vector, we will use our generative model to produce a valid looking vector and then pass it through a decoder, and that's your final image. So this is basically the philosophy of how and what the latent diffusion model is trying to do. Now I would like to I would like try to avoid very much mathematical details, but one thing that I would really like is if you can appreciate how beautiful this whole process is. And for that there will be some kind of math there, but it's going to be very simple, I promise. So let's start with the basic concept that I iterated before as well. So we have two distributions here again, but I have mapped all of this into much more lower dimensions so that you can visualize. So we have blue is our source distribution, and what the model is doing is we have a target distribution, and model is just mapping that distribution to our target distribution, right? How the model will do that, we will see that briefly as well. But as a result of this distribution mapping, it's much more intuitive to visualize is in the form of the data samples. So previously we were looking at distribution density, but it's not very intuitive to visualize it. Much more intuitive is if we look at the data samples. So you see, this is where my noisy data resides. So the noisy data resides at my normal distribution. It's somewhere close to the origin, and model is going to map that normal distribution to my target distribution. And my target distribution, which we see in this orange color, is going to be a valid looking sample. So if I pick anything from that orange point, it is going to be my valid data point. So I would like to now explain what that orange data sample actually looks like in practice. So now we are bringing that whole philosophy to the avatar creation process. So we are tying it together. As I explained in the beginning, avatar has three main things: identity, pose, expressions, right? The target data distribution that we are seeing here in the orange basically is this motion vector, which is my target data distribution. And the motion vector contains pose and expressions, right? And my output is going to be identity of some person plus the motion vector that I'm going to sample from this particular point, right? So at the end of the day, what the model is going to learn is this particular motion vector from the data distribution. And that motion vector will represent a facial performance, meaning it could be smiling face, angry, articulating a certain phoneme. It can be any facial performance. Now, the one thing that I just explained is because it's going to be a particular motion vector, the sampling will look something like this. So I pick any random point from my target distribution, it will have a certain kind of expression. If I pick a different point from my target distribution, it is going to have a different set of expression. But please keep in mind, here we are fixing the identity. It can be any identity, and whatever I will sample from here is going to have a motion vector. So if I sample a smile, I can make any identity smile with the help of the encoder decoder that we learned previously. What the model is going to do, here we start to kind of trigger the training process, and the training process will look like this. So the model will start from a very noisy distribution, And for every point that we have the noise, we will ask the model to move that point toward my actual distribution. And this is going to be an iterative process. We will design a loss function or a reward function around it, and we will iterate it a lot until we arrive at convergence. So until we see that the point that I'm sampling is much closer to my ground truth data. And this is going to be an iterative process, and this is how the model is going to eventually map any source distribution to the target distribution. And once this process is done, as a result of it, this is something that is created that we call flow field. So this flow field is dictating the flow of the data, right? If I sample any point in space, the flow field will dictate where I should move. And that will help me arrive at my target distribution. So this is what the flow matching basically as a loss function does. And once you have learned this flow field, the sampling process becomes very easy. So you have a model that you have already trained. You pick a random point in your noise area. That random point we give to the model. The model will tell, okay, this is how much you should move. And then in this direction, you will actually arrive at your target distribution. So this is what the sampling process will look like. It's iterative, and the number of iterations, the more the number of iterations, the better your final arrival will be. And so by iterating this multiple times, we will be able to sample valid looking expressions starting from like a random noise that had no information whatsoever. And this is how the sampling will look like. So for every point that we want to sample, we will start with the noise region, we will map it to the target distribution, and we will get a valid looking expression. So this is after the generative model has been trained, this is how it's going to look like, right? But there's one caveat. Sampling it just with this randomly and does not add any value. Because what we are looking for here is we want to create performances or the articulation or the facial movements that match some audio signal, because we want to create talking head avatar, right? And that's where the audio modality comes in, or an additional modality comes in. We won't go too much into detail of what that looks like. Maybe that would be another talk next time, so stay tuned. But what actually happens here is you get an audio signal, and when you are actually in this stage, when you are sampling a point, along with that point, you also pass your audio vector to this model, right? And when you pass that, where the sample point is supposed to go, that flow field is going to be dictated by that audio feature as well, right? So you have audio feature guiding the flow of the noisy to the target distribution. And with the help of that guiding or the condition on the audio, you start to get valid looking expressions that are conditioned on that audio vector. At this point, this model becomes a sequence to sequence model. So meaning that you have a window of audio, and at the output, you get window of the motion vector. So the model is going to predict, let's say, 5 target data points instead of just one, which we were doing previously. And with the help of those consecutive points, you will get a seamless looking performance, as you see here, where the person is trying to, the lips are moving in a rhythmic manner and is trying to match the audio signal that we have here. So this is how you add additional modality. I will quickly, try to explain what the training process actually looks like, which we touched on here, where we were trying to map to the target distribution, what it looks like in practice. So we have 2 stages, which we looked at previously as well. The stage 1 is going to be just the encoding. So we are trying to learn a latent space which encodes the identity, pose, and expression of a human head, right? We encode that into a latent space, and the way that we do this is we have an encoder, decoder, and with the help of the decoder, we just simply try to recreate what we pass to the encoder. And that's how we learn the latent space. And in the second stage, once the first step is done, we try to learn the audio to latent, we call it audio to latent network. Now, this is the generative network, which we have been talking about so far. This particular component arrives in stage 2. And as you can see, the audio to latent is trained to match such that whatever latents we will predict should match the latents that the encoder is predicting, right? So given an audio signal that you see here, we will have the corresponding video of the person from which we have extracted that audio, right? So that audio we will pass through our generative network, and that generative model is going to give us a performance, and we would like that performance to match whatever the encoder is producing from an actual video. And that's just how the training of this two-stage setup is done. And once the training is done, this is what it boils down to. The whole process becomes much more simpler. You have an audio signal. You have trained your generative model. It is giving you a performance in the form of latents, and you have a decoder to which you will pass the identity and your performance, and then you will get an avatar that has the facial appearance and geometry and structure of that particular identity, and you are speaking the audio signal of whatever the audio to latent is producing. One thing that I would like to show now, if this would let me, let me just quickly maybe reload it. Okay, now we can see it, right? Okay, so at the end of the day, this is pretty much what it looks like. So the whole process has been boiled down to just one image as an input and an avatar performance.
Hello, everyone. I hope you enjoyed the presentation.
So you can technically make this image say anything. And as you saw previously, when we started off with when we were trying to model the head initially, there was a lot of steps involved. It has a lot of different stages. We were trying to model the head and then fit the face model. But all of that is encapsulated in these two stages, which we have trained and is much more scalable, because for every new person, we don't have to repeat the process. The details of the model have encapsulated it. Okay. So I would like to conclude this by sharing a little bit about how this whole thing is evolving and what's next. So this whole avatar domain actually started with simple lip sync, where you had videos and then you were trying to match the lip movements to whatever the new audio or novel audio we have, right? And then the very interesting thing that's added and then something that we have been working on is emotion. So whenever we are communicating, we just don't communicate through our lips. There's a lot that happens through the full facial expressions, the way that we communicate. And that's what this generative AI model that I discussed was representing. So it was representing the full face performance rather than just the lip movements. But beyond that, there are very interesting exploratory direction where you could train the models to not only speak but listen. And that will help us put together very engaging conversation scenarios. So have two avatars speaking to each other, and when the model will take both audios as an input, because when one avatar is not speaking, it's listening, and then the performance has to be reactive. It should look like it's attentive. It should nod or say no, and these kind of things. That is going to be a very interesting research direction. And after that, there is a room for a lot more with vision as a modality. For example, having the avatar not just listen and speak, but also see what is in the environment and move according to that or react according to that. So the space is just getting started, and there is a lot that needs to be done, and a lot of interesting research directions will pop up. And yeah, so this is what the conclusion I would like to make. So thank you.